Come on, my dears, let us begin with chapter number 6. Title is Nucleus. See, the previous chapter was based upon atom. Now we go very much in detail in the interior part of atom, in the central part of atom called nucleus. Correct? Let us recall what you had studied about nucleus in the previous chapter. What do you mean by nucleus? Mr. Rutherford had proved on his experiments on alpha scattering. He had proved from those experiments that, he concluded from those experiments that the central part of an atom is very tiny, very heavy. It consists of almost total mass of atom and it consists of total positive charge of an atom. Such a tiny, heavy central part of an atom is termed as nucleus. Correct? Almost a total mass of an atom and total positive charge of an atom are found to be concentrated in the very tiny central part of an atom called nucleus. Simple? Fine. Now, among the atoms of all different elements, which is that atom which is the lightest? It is found to be atom of hydrogen. Atom of hydrogen, correct? Simple hydrogen, correct? We have isotope of hydrogen whose atoms are heavier than hydrogen atom. They are deuterium. They are deuterium. In the nucleus of hydrogen atom, there is only one proton. But in the nucleus of deuterium atom, there is one proton and one neutron also. Still heavier isotope is there. It is called tritium. In the nucleus of tritium atom, there is one proton and two neutrons. Okay. But right now we are talking about simple hydrogen and it has only one proton in the nucleus. It is found to be the lightest atom among all the atoms of different elements. Fine. And you know very much that proton and neutron, they are the fundamental particles. They reside inside the nucleus. Because both of them are residing inside the nucleus, we have given a common name to both of them, and that common name is called nucleon. Nucleon is a word which you can use for proton also, for neutron also. See, now onwards in this chapter, we are going to concentrate on the study of different nuclei, and when we concentrate on the study of a particular nucleus, that particular nucleus is given another name. It will be now onwards known as nuclide. So whether it's a nuclide or you are just focusing on a particular nucleus, it is one and same. Okay. Nucleus, another name of nucleus is nuclide. Okay. What is the symbol of nucleus? Very simple. Either symbol of nucleus you may choose this way or this way. In the textbook they have chosen this way. Okay. ZXA or this way, ZXA. What is X? It is chemical symbol of given element. Chemical symbol of given element. What is Z? Atomic number. What is Z? Atomic number of a given element. And that atomic number gives you number of protons in the nucleus of one atom of a given element. And because atom is electrically neutral, whatever is the number of protons in the nucleus, same is the number of electrons outside the nucleus. Correct? Protons are inside the nucleus, electrons are outside the nucleus. Correct? For a neutral atom, number of protons and number of electrons are same. So Z indicates both. It indicates number of protons also and it indicates number of electrons also if atom is electrically neutral. Fine. Then what about capital A? Capital A is the number which is written at the top. It gives you total number of protons and neutrons. Total number of protons and neutrons, we call it atomic mass number. We call it atomic mass number. Fine. It is shown by symbol capital A. It gives you summation of number of protons and neutrons. Fine. Now tell me, what will be number of neutrons from this? It will be A minus Z. A minus Z. So when you make subtraction this way, this minus this, it will give you number of neutrons. Got it? And when number of protons and number of neutrons are added, it will give you total number of nucleons. Total number of nucleons which is generally known as nucleon number. Nucleon number and atomic mass number, they are one and same. Now let us see some of the definitions. If you prepare this table, then all the 4 definitions you can remember very easily. Let us see one by one. First of all, we will see the definition of isotopes, then isobars, isotones, isomers. All the definitions start with the same phrase of the words. What is that phrase I am showing you? It is atoms for the nuclei of which. How would you start each of these 4 definitions? Atoms for the nuclei of which. Atoms for the nuclei of which. Look, here I have written whatever is same. Here I have written whatever is different. And here I have given some of the examples. Okay, let us see one by one. Come on, first of all, for isotopes. Atoms for the nuclei of which atomic number is same but atomic mass number is different are called isotopes of a given element. I repeat. Atoms for the nuclei of which atomic number is same but atomic mass number is different are called isotopes of a given element. See the example. 6C12, 6C13, 6C14, correct? Written below it is Z, and you can see Z is same everywhere. Written above it is A is different, 12, 13, 14, A is different, Z is same, A is different. They are called isotopes of given element. Given element is right now carbon. Simple. Now let's go for what is called isobars. Very simple. Start with the same phrase of the words. Atoms for the nuclei of which atomic mass number is same but atomic number is different are called isobars of each other. Are called isobars of each other. For example, 83 bismuth 210, 84 polonium 210. Come on, Z is different. Z is different. But written at the above, come on, above this symbol. What is it? 210 here also, 210 here also. So atomic mass number is same. Atoms for the nuclei of which atomic mass number is same but atomic number is different are called isobars of each other. Fine. Come on, isotones. What are called isotones? Atoms for the nuclei of which number of neutrons is same but atomic mass number and atomic number are different are called isotones of each other. Come on, examples. 36 krypton 86, 36 krypton 86, 37 rubidium 87. You can see Z is different, A is also different. Z is different, A is also different. But what is number of neutrons? It is A minus Z. N equals to A minus Z. N equals to A minus Z. This minus this, how much it is? 50 will give you number of neutrons. And this minus this is also 50. So here also number of neutrons is 50. Here also 50. Number of neutrons is same. They are called isotones of each other. Come on, last definition now, isomers. Atoms for the nuclei of which number of neutrons, atomic mass number, everything is same, but their radioactive properties are different are called isomers of each other. For example, 35 bromine 80. This element has got one pair of isomers. If you have got this element and if you are comparing two atoms of the same element, then both the atoms have got everything same. Atomic number is same, atomic mass number is same, number of neutrons is same, but their radioactive properties are different. That's why they are called isomers of each other. Simple. What do you mean by atomic mass unit? Atomic mass unit. It is shown by symbol small u. See, in the study of nuclear physics, we are going to deal with very tiny particles, and those atomic particles have got very small mass. So, to measure their masses, naturally kilogram will be very heavy unit, and that's why we define very small unit of mass, and here it is atomic mass unit shown by symbol small u. How much mass is one atomic mass unit? I am showing you. Practically we find that mass of one carbon atom is this many kilogram. See the figure, 1.992647 into 10 raised minus 26 kilogram. Now this mass of one atom of carbon, if it is divided by 12, then whatever is the mass is called 1 atomic mass unit. But mind well that carbon atoms should be neutral and unexcited. Neutral and unexcited. So now define what is called 1 atomic mass unit. 12th part of mass of neutral and unexcited 6C12 carbon atom is called 1 atomic mass unit. I repeat, 12th part of mass of neutral and unexcited 6C12 carbon atom is called 1 atomic mass unit, shown by symbol small u. Now when you divide this many kilogram by 12, the answer is 1.660539 into 10 raised minus 27 kilogram. Correct? Fine. What about mass spectrometer? We have got one very good device in laboratory called mass spectrometer. Using this device called mass spectrometer, we can determine mass of atom of different elements. That device is called mass spectrometer. Now using this device, when we measure masses, you know what the fact we have come to know? Every element whichever is found in nature is found to be composed of its more than one isotopes. Okay? So when every element is made up of more than one isotopes in a mixture, how would you determine mass of a single atom? For that, to find out mass of a single atom, we just go for finding weighted average. Weighted average. Then you may ask, sir, what is weighted average? I am showing you. In textbook, they have considered an example of 2 isotopes in a mixture. But in general, suppose there are n number of isotopes in a mixture. N number of isotopes in a mixture. Then what is the weighted average of those masses? I am showing you. Suppose first isotope is there, in which mass of every atom in first isotope I am taking as M1. Its proportion is suppose X1 percentage. Mass of each atom in second isotope is M2. Its proportion I am taking X2 percentage. Similarly, mass of one atom in nth isotope is suppose Mn and its proportion is suppose Xn percentage. Then you just find out such a summation and divide it by x1 plus x2 plus dash 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 plus xn, and where this denominator is always 100, because whatever is the quantity in a given mixture, that quantity we take as total, that is 100 percentage. Okay, fine. Now for example, mass of one chlorine atom, how would you find out? Mass of one chlorine atom, how would you find out? I am showing you. Because chlorine has only 2 isotopes, stop this addition at second term. Stop this addition as second term. So what do you write? M1x1 plus M2x2 upon x1 plus x2. M1x1 plus M2x2 upon x1 plus x2. Wait. What is M1? Mass of each atom in first isotope. It is found to be 34.98 atomic mass unit. And its proportion is found to be 75.4 percentage. Don't remember these values. Whenever required, they will give you in the numerical example. Okay? Don't try to remember. Come on. What is this 36.98? It is M2. Means mass of each atom in the second isotope in atomic mass unit. And what is this 24.6? The proportion of second isotope in a given mixture. And denominator is x1 plus x2. As I said, if you stop this addition at second term, then x1 plus x2 will be 100. So I am just dividing by 100. Now simplify this. This into this is this much. This into this is this much. And this summation divided by 100. Answer is 35.472. This many atomic mass unit. What is this? Mass of single chlorine atom. Mass of single chlorine atom. Got it? See, if you got mass of one chlorine atom 34.98 atomic mass unit. This is nearly 35. Then that corresponding isotope is shown by this symbol 17 chlorine 35. 17 chlorine 35. And if you got mass of chlorine atom 36.98 atomic mass unit, which is nearly 37 atomic mass unit, then that particular isotope is shown by this symbol 17 chlorine 37. Correct? This is that isotope in which mass of each chlorine atom is this many atomic mass unit. This is that isotope of chlorine in which mass of each chlorine atom is this many atomic mass unit. Got it? Fine. What about neutron? History says that in the year 1932, there was an experimenter, Mr. Chadwick. He was a physicist, Mr. Chadwick, and he had proved experimentally that whenever beryllium, this element beryllium, is bombarded by alpha particles means nuclei of helium atoms. A nucleus of helium atom is called alpha particle. When this beryllium is bombarded by alpha particle, at that time Mr. Chadwick had proved that one particle is emitted, it is found to be electrically neutral and its mass is nearly equal to mass of proton. That same particle is what given a name, it is known as neutron. Correct? So who had discovered neutron? Mr. Chadwick had discovered neutron, and just for the same discovery he was given a Nobel Prize. He was rewarded with a Nobel Prize. Correct? Let me remind once again. Come on, when beryllium is bombarded by alpha particles, the resultant nucleus is found to be such that it emits one particle. That particle is found to be electrically neutral and it is also having mass nearly equal to mass of proton. Such a particle is known as neutron. It was discovered by Mr. Chadwick. Okay, this reaction is not given in the textbook, just for your kind knowledge. This beryllium is bombarded by alpha particle. Beryllium means 4, beryllium 9. Alpha particle means helium nucleus 2He4, and it gives neutron. Symbol of neutron is this 0 and 1. Come on, 4 plus 2 is 6. 6 minus 0 is 6. Come on, 9 plus 4 13. 13 minus 1, that is 12. Okay, fine. Now kindly read this statement of first illustration. Read it? Look. Mass of one boron atom, they have given in the statement 10.811 atomic mass unit. Now they have given two isotopes of boron. One is 5 boron 10, another is 5 boron 11. Now mass of each boron atom in this isotope is 10.01294 atomic mass unit, and its a percentage, its a proportion in a given mixture is suppose x1 percentage. Mass of each boron atom in this isotope 5 boron 11 is, they have given this much, 11.00931 atomic mass unit, and its proportion in a given mixture is suppose x2 percentage. Come on, from this general formula, if a given mixture has only two isotopes, then you will stop this addition at second term, and then formula will appear like this: m equals to m1 x1 plus m2 x2 upon x1 plus x2, which is 100. Okay, fine. Now tell me, m1 x1 as it is, m2 as it is, but what about x2? Because x1 plus x2 equals to 100, then x2 will be, come on, 100 minus x1. x2 will be 100 minus x1. Correct? Now tell me, this is mass of one boron atom which they found out by weighted average, and that mass they have given 10.811 atomic mass unit. What is this? mass of each boron atom in the first isotope, which they are given 10.01294 atomic mass unit, into x1. What is x1? Proportion of this first isotope in a given mixture. Fine. Come on, M2. What is M2? Mass of each boron atom in the second isotope, which they are given 11.00931 atomic mass unit, into 100 minus x1 as it is, divided by 100 as it is. Simplify and find out value of x1. If you find out value of x1, it comes out to be 19.9, that many percentage. Why percentage? See, this is 100 is in percentage. Okay, so from percentage, what value you can subtract? Percentage only. So x1 comes out to be 19.9 percentage. Now what is x2? x2 was 100 minus x1. Percentage wise 100 percentage minus percentage of x1 is how much? 19.9. So 100% minus 19.9 will give you answer 80.1 percentage. Okay. So this is your final answer. So now tell me, proportion of first isotope is x1 percentage, which is 19.9 percentage. Proportion of second isotope is x2 percentage, which is 80.1 percentage. Got it? Now this note I have made here. If you can remember, you can. If you cannot remember, don't bother. Whenever required, they will give you in the numericals. See, mass of electron everybody knows, 9.1 into 10 minus 31 kilogram. But suppose they ask in atomic mass unit, what will you do? Going from atomic mass unit to kilogram, you will multiply by this factor. Just speak reverse. When you want to go from kilogram to atomic mass unit, you will divide by this factor. So when you divide this value by this factor, correct, you will get this answer, 0.00055 atomic mass unit. Similarly, mass of proton is this many kilogram, this many atomic mass unit, and mass of neutron is slightly greater than this mass. It is this many kilogram and this many atomic mass unit. Okay, don't try to remember, correct? Whenever required, they will give you in the numerical statement. Okay, thank you. Come on, my dears, let us proceed further in chapter number 6. Today, the first article is about nuclear forces. Fine. Nuclear forces. Tell me, how much is the size of nucleus? Is it not very small? Yes, it is extremely small. Then in that extremely small volume, there are protons and neutrons which are residing together. Then up till now, there must have arisen some question in your mind regarding their so much close existence, because neutrons do not have charge, but protons, they have positive charge. And when so many protons are residing so much close to each other inside the nucleus, naturally you should think that how they can manage to remain so much close, because when there are two protons, both of them have positive charges, so they are like charges, and you know like charges always repel each other, and this repulsive force is known as Columbian force, which is of long range type. So naturally question arises, when there are long range repulsive forces between the protons inside the nucleus, how they can stay so close to each other? How? Experiments have proved that though there are very strong repulsive forces between the protons inside the nucleus, then also they can remain within the nucleus. It means to say that along with these repulsive forces, there must be prevailing enough attractive forces also, which can balance that strong repulsive forces. Yes, experiments have proved that, yes, really these attractive forces are prevailing between the nucleons, which can balance that repulsive force. And when attractive forces balance repulsive forces, then nucleons can remain so close to each other, and that is why they remain in a bound state in the form of a stable nucleus. Correct. And when further research was made we came to know that such forces which are of attractive type prevailing between the nucleons inside the nucleus do not depend on electric charge, means they are charge independent, and when they are charge independent, such forces can be exerted between two protons also, between two neutrons also, between one proton and one neutron also. In short, between two nucleons such forces are prevailing in the form of attractive forces. Fine. And we also came to know that these attractive forces are effective up to very short distances. That's why we call them short range attractive forces. Correct? Such forces which are prevailing between the nucleons existing only inside the nucleus are only known as nuclear forces. And because they are stronger than electromagnetic, stronger than weak forces, stronger than gravitational forces, we have given another name to these nuclear forces as strong forces. Correct? Fine. How would you define these nuclear forces? Very simple. Short range attractive type of forces acting between proton-proton, proton-neutron and neutron-neutron, which bind all the nucleons together, are called nuclear forces. I repeat, these short range attractive type of forces acting between proton-proton, proton-neutron and neutron-neutron, which bind all the nucleons together, are called nuclear forces. Fine. Now let us see some of the characteristic features, some of the specialities of these nuclear forces. First, as I told you, it is the strongest, and that's why they are also called strong forces. Stronger than electromagnetic forces, stronger than weak forces, stronger than gravitational forces. Fine. Second point, they are present only inside the nucleus. They are not present outside the nucleus. Okay? They are restricted within the nucleus only. Fine. They do not depend on charge, so they are found to be charge independent. Then they are effective up to very short distances. That's why they are called short range forces. And the nuclear forces are present in the very small region, correct? So every nucleon is capable of exerting these nuclear forces only on the very closely lying neighboring nucleons only, and within that very short range they are satisfied. They are satisfied. They are saturated. That's why this fact is called property of saturation. Property of saturation. Property of saturation is that because of this property you can say nucleons, they get satisfied, they get saturated while exerting forces, nuclear forces on very closely lying neighboring nucleons only. Fine. Then we have come to know that these nuclear forces between two nucleons, if the distance between two nucleons is more than 0.8 Fermi, Fermi or femtometer shown by symbol small f small m, and you must have remembered 1 Fermi means 10 raised to minus 15 meter. When distance between two nucleons is more than 0.8 Fermi and less than 3 Fermi, the nuclear forces are found to be of attractive type. And when distance between two nucleons is greater than 0 but less than 0.8 Fermi, at that time the nuclear forces are found to be repulsive type. But though there are repulsive type nuclear forces, though there are attractive type of nuclear forces inside the nucleus, the resultant force is in the form of attraction. That's why you may regard nuclear forces as if overall effect, if you see, overall effect is of attraction only. That's why we say nuclear forces are majority attractive. Fine. Then nowadays these nuclear forces are not considered as fundamental forces. Earlier nuclear forces were considered as fundamental forces, but now we have come to know that neutron and proton inside the nucleus, they are made up of further smaller, more fundamental particles called quarks. So they have their own quark composition. Because neutron and proton are made up of quarks, then whatever is the interaction forces between two nucleons, actually those interaction forces are between two quarks. So we regard these nuclear forces now onwards as quark-quark forces, and such quark-quark forces are taken nowadays as fundamental forces. Instead of nuclear forces, now quark-quark forces are said to be fundamental forces. There are 6 types of quarks we have found so far, and those 6 types are, you are supposed to remember their names: up quark, down quark, charm quark, strange quark, top quark and bottom quark. Up, down, charm, strange, up and top and bottom. I repeat, up quark, down quark, charm quark, strange quark, top quark and bottom quark. There are 6 types of quarks, correct? And whenever we have found the quarks, they have always been combined in a group of minimum 3 quarks, okay? So far we haven't got independent existence of single quark. Single quark does not exist independently. It has quarks always have been found in a group of minimum 3 quarks, okay? Fine. Then the 7th noteworthy point regarding nuclear forces, they depend on the orientation of spin of nucleon. Each nucleon inside the nucleus performs spinning motion about an axis passing through itself, correct? About its own axis, they spin, and depending upon the arrangement of that axis of rotation, depending upon the orientation of axis of rotation for different nuclei, different nucleons, then the corresponding nuclear forces would change. Nuclear forces between two nucleons depend on the orientation of axis of rotation for their spinning motion, okay? Fine. Then this point is not there in the textbook, but just for your kind knowledge, nuclear forces are found to be non-conservative. Nuclear forces are found to be non-conservative. And so far, we haven't got any simplified formula to express nuclear forces. The way you have simple formula for Columbian forces, for gravitational forces, that way simplified form of nuclear force so far we haven't got, okay? Fine. Now let us see one extra question. Tell me some points of difference between nuclear forces and Columbian forces. First point, between nuclear forces and Columbian forces. First point, nuclear forces are majority attractive, correct? Columbian forces may be attractive, may be repulsive. Nuclear forces are prevailing only inside the nucleus. Columbian forces are present inside the nucleus also, outside the nucleus also, correct? Then nuclear forces are of short range type. Columbian forces are of long range type. Nuclear forces do not depend on charge. Columbian forces, they depend on charge. Nuclear forces do not obey Coulomb's law. Columbian forces obey Coulomb's law, correct? So there are very good points of difference between nuclear forces and Columbian forces. Got it? Fine. Now let us see one graph. In textbook they have simply given that graph, not at all explained. I will explain you, just concentrate here. The potential energy of a system of two nucleons separated by distance r, I have taken in this graph on y-axis, and the distance between two nucleons measured in Fermi I have taken on x-axis. Fine. So this potential energy is a function of distance r between two nucleons. That graph is found to be like this. Look, you must show same shape in the examination. You must not change the shape, okay? Retain the same shape. Fine. Now tell me, what does this graph indicate? Here potential energy is 0. As you go on upper side this way, potential energy values are positive. When you go on lower sides, come on, potential energy values are negative. Fine. Now tell me, here is that much separation between two nucleons with value 0.8 Fermi. It is such a separation at which the potential energy is found to be minimum. And when potential energy is minimum, the stability is maximum. Fine. And that distance 0.8 Fermi is known as average internucleon distance. Average internucleon distance, correct? Now let us see what would happen if distance between two nucleons is smaller than this distance and greater than this distance. What will happen? I am showing you. See, if you decrease this value of R smaller than 0.8 Fermi, then you are likely to go this way, look here, this way, because distance R decreases. And when you are going on this side, distance between two nucleons is less than 0.8 Fermi. At that time, the nuclear forces are found to be repulsive. Repulsive. Why? I am showing you. When you go this way, the value of potential energy increases from negative to 0 and 0 to positive. Look, negative to 0, 0 to positive. Ultimately, potential energy increases. At that time, the nuclear forces between two nucleons must be repulsive. Why? I am showing you. Though there are repulsive type of nuclear forces between two nucleons, if they tend to move towards each other such that separation between them is decreasing and becoming smaller than 0.8 Fermi, then at that time both the nucleons will require to do work against these repulsive forces, and in doing that work their kinetic energy will be utilized, and so kinetic energy will decrease, and the decrease in kinetic energy is converted into increase in potential energy. That's why this potential energy of the system goes on increasing from negative to 0, 0 to positive. Simple? Fine. And now you think of this case when separation between two nucleons is becoming greater than 0.8 Fermi. When R value increases beyond 0.8 Fermi, I say internucleon nuclear forces are of attractive type. How? I am showing you. See, when you go this way, then potential energy curve rises this way. It means to say potential energy value is going to become from negative to 0, correct? From negative to 0. So potential energy is increasing. You know how it is increasing? I am showing you. When separation between two nucleons is becoming greater than 0.8 Fermi, at that time the forces between them are of attractive type. Then also if nucleons manage to move away from each other, then they will require to do work against these attractive forces. So when they have to do work, means their kinetic energy will be utilized, and then kinetic energy will decrease, and at the cost of that kinetic energy, potential energy of the system would increase. That's why potential energy is increasing from negative. Gradually it is becoming less and less negative and trying to become towards 0. Okay, this value is increasing from negative value to towards nearly equal to 0. Correct? Fine. So when separation between two nucleons is less than 0.8 Fermi, at that time internucleon forces are repulsive, and when separation between two nucleons is more than 0.8 Fermi, at that time internucleon forces are attractive. Got it? Fine. Now in this part of the graph, look here. In this part of the graph, how does potential energy of a system made up of two nucleons separated by distance r changes with separation r? How? According to which formula? That formula I have written here. U as a function of r is found to be equal to minus g square into e raised to minus small r upon capital R upon r. Capital R and G, they are constants. Small r is the separation between two nucleons. Fine. Here this part G square is altogether, G square is known as strength parameter. What is it called? Strength parameter. That is what they have written in textbook. But if you are asked to find out unit of strength parameter, how would you find out that unit? Very simple. See, if any power is there to the base E, that whole term will not have any unit. So this part is unitless. Fine. And now if you want unit of G square, you must transfer this R here. So it is energy into distance. Energy into distance. Unit of energy is joule. Unit of distance is meters. Correct? Fine. What about dimensional formula? Dimensional formula of G square would be that of work multiplied by square of distance. For work, what is the dimensional formula? M raised to 1, L raised to 2, T raised to minus 2 into distance. So L, correct? Now M raised to 1, L raised to 2 plus 1, 3, T raised to minus 2. M raised to 1, L raised to 3, T raised to minus 2 is now dimensional formula for strength parameter, that is G square. Correct? Fine. Now let us see another short note about nuclear radius. Correct? Through the experiments performed by Rutherford on alpha scattering, we could have very first estimation that nuclear radius is estimated to be of the order of 10 raised to minus 15 meter. Correct? Now let us see how is the distribution of material inside the nucleus. How is the distribution? How much is the density? Correct? Let us see that. Look. This figure I have drawn here just for your kind knowledge and satisfaction. You are not supposed to draw this figure in the examination. It is not there in the textbook. Okay? The distribution of material inside the nucleus, we find something like this. Up to certain distance from the center of nucleus, the material is found to be spread with almost uniform and constant density. That's why the shade is uniform. In this volume, the shade is uniform. But further, if you move away, then density goes on decreasing. Fine. And at certain distance, density becomes almost zero. We cannot come to know where exactly density becomes zero, that we cannot come to know. That's why the nucleus does not have characteristic or specific surface. There is no characteristic or specific surface of the nucleus. Correct? Now, whatever explanation I gave you in this diagram, if you want to give the same explanation using some graph, then that graph is there in our syllabus, in our textbook. You must remember this graph. Very simple. On y-axis, I have taken density of material of nucleus as a function of distance from the center of the nucleus versus distance from the center of nucleus. This graph is found to be like this. Look here. Correct? Fine. So what does it indicate? Up to certain distance, density is almost constant. Okay, almost constant. And further, if you move away, then this density goes on decreasing. Fine. Correct? It decreases to almost zero. Fine. Now, in this case, when density is not uniform throughout the entire volume of the nucleus, how do we define radius of a nucleus? We define radius of a nucleus in a definite way. What is that? I am showing you. We define characteristic or effective radius. Characteristic or effective radius of a nucleus. The formula of characteristic or effective radius of a nucleus is determined empirically. Throughout, by following the practical observations, we have just set mathematically that formula of characteristic or radius of nucleus. This average radius or effective radius or characteristic radius, how do we determine? We determine using one formula which is called empirical formula. Okay, and that empirical formula is derived on the basis of experimental observations. What we do, we just set theoretically and mathematically that formula of R the values of radius obtained from which are consistent with the practically observed values. Okay, then that formula is called empirical formula. Okay, a formula which is derived on the basis of mathematical adjustment, trial and error, and using the practically observed values. Such a formula is called empirical formula. Empirical formula for finding characteristic or effective radius of nucleus is R equals to R0 into A raised to 1 by 3. Wait, what is capital A? It is called atomic mass number. What is R0? It is constant. Its value is ranging between 1.1 Fermi to 1.2 Fermi. Its value is how much? 1.1 Fermi to 1.2 Fermi. In all the numericals now onwards, we will take value of R0 as 1.1 Fermi. Okay, fine. Now, what is called average radius of nucleus? Correct? Simple. You start with this much density, you move away from the center of the nucleus, and at certain distance it will so happen that this density would become half of maximum density, that is 50% of density at the center. Correct? That much distance from the center of nucleus is known as average radius. Correct? Fine. There is one more radius which is defined this way. It is interaction radius. See, what will be the value of R0? That depends on through which experiments you are finding the value of R. If you are finding the value of R using the experiments in which there are collisions between electron and nucleus, then value of R determined is known as average radius. The radius of nucleus determined in the experiment where there is a collision between electron and nucleus is called average radius, and the value of radius of nucleus determined from the experiment in which there is a collision between alpha particle and nucleus is called interaction radius. Depending upon which radius you are finding, we have to take different values of R0. Okay, fine. What about value of density of nucleus? Value of density of nucleus is found to be very large, as high as 2.3 into 10 raised to 17 kilogram upon meter cube. 2.3 into 10 raised to 17 kilogram upon meter cube. You can rewrite this way: 2.3 into 10 raised to 14 into 10 raised to 3 kilogram upon meter cube. Fine. But now tell me, what is this 10 raised to 3 kilogram upon meter cube? It is 1000 kilogram upon meter cube. It is nothing but density of water. So remember, density of material of nucleus is 2.3 into 10 raised to 14 times the density of water. Okay, fine. Then we go for another article called stability of nucleus. Let us discuss about stability of nucleus. Different nuclei have different stability. How do we measure it? I am showing you. Consider first of all nucleus of light element. Say for example 6C12 carbon nucleus. Just compare it with ZXA. Then you will get Z equals to 6. Correct? And number of protons is 6. What about number of neutrons? It is A minus Z. So it is 12 minus 6. 12 minus 6, that is 6. So in the nucleus of carbon atom, there are 6 protons and 6 neutrons. Whatever is number of protons, same is the number of neutrons. So you can say number of protons and number of neutrons are equal, meaning thereby N equals to Z. Got it? Fine. Then if you take Z in the denominator, then N upon Z will be equal to 1. But this is true for nucleus of light element. Let us see what is the case for nucleus of heavy element. Come on. Nucleus of heavy element. We take this nucleus 82 Pb 208, match it with ZXA, then Z equals to 82, number of protons is 82. What about number of neutrons? It is A minus Z, so it is this minus this, it is this minus this, answer is 126. This number is greater than this number by 44, okay, this minus this, answer is 44. So number of neutrons in the nucleus of lead element is greater than number of protons by amount 44. In short, this number is greater than this number, that is sure. So n is greater than z. When n is greater than z, n upon z would be greater than 1. But why? For a nucleus of light element, n equals to z, and for a nucleus of heavy element, n is greater than z. Why? What is the reason? I am showing you that reason. Look. So now let us try to understand why there are more number of neutrons than the number of protons inside the nucleus of heavy element. Why? What is the reason? I am showing you. Consider a nucleus of light element which is right now stable. Stable means no nucleon is coming out. No nucleon is coming out of the nucleus. Okay, fine. But tell me, in the periodic table, as you move from lighter to heavier element, you know, atomic number increases. When atomic number is increasing, number of protons inside the nucleus will increase. Let us increase that number by 1. I am just increasing 1 proton in this stable nucleus. Look, when you are adding 1 proton, both the forces will increase. Columbian repulsive force also will increase and nuclear attractive force also will increase. But you know, nuclear forces are short range forces. So this would exert attractive forces only on neighboring nucleons. But at the same time, it would exert long range Columbian forces on all these remaining protons. And then because of that repulsive forces, what should happen? These all protons should come out of the nucleus. If protons would come out of the nucleus, then nucleus will become unstable. But even the nucleus of heavy element is also stable. So what does it mean? That because of inclusion of 1 proton, whatever is the increase in repulsive forces, same must be increase in attractive forces. So now tell me, if you want to make this nucleus once again stable, what you should do? You should compensate that increase in repulsive forces. To compensate increase in repulsive forces, you need to increase attractive forces. And for that, you may think of adding neutron. Look, if I am adding 1 neutron here, no doubt it will exert attractive nuclear forces, but only on the neighboring nucleons, because nuclear forces are short range forces. So from this region, enough attractive force will be prevailing so that no nucleon will go out of this region. But what about these far regions? Correct? If you want to have the nucleons bound in those regions also, then you need to add 1 neutron in each small part of the nucleus. So when you add 1 neutron in each small part of the nucleus this way, then enough attractive force will increase in the entire volume of the nucleus, which will compensate that increase in repulsive force. And ultimately, when no nucleon is escaping out of the nucleus, meaning thereby nucleus has become more stable. Correct? Tell me, whatever instability was caused by addition of 1 proton, just to have the same stability once again, we need to add more than 1 neutrons. So in this process, you can see number of neutrons will be greater than number of protons. Number of neutrons will be greater than number of protons. Nucleus of heavy element can remain stable only when number of neutrons is greater than number of protons. So this n greater than z becomes the necessary condition for the stability of nucleus of heavy element. Nucleus of heavy element can remain stable only if n is greater than z. Fine. Now here in this graph of z versus n, I have plotted one straight line, correct? Exactly at 45-degree angle with x-axis or with y-axis. For any point on this straight line graph, the x and y coordinates are same, that is n equals to z. So this line is called n equal to z line. Now we have also plotted another curve, that is blue colored dotted curve. Now for this blue colored dotted curve, you can see its initial part is superposing on this straight line, which is n equal to z, meaning thereby for these points which are in the initial part of this dotted curve, n equals to z, meaning thereby you are talking about nucleus of light element. Fine. And then when you take points here, for such points this x coordinate is more than y coordinate, that is n is greater than z. That's why I am writing n greater than z. Correct? And because the positions of stable nuclei are found to be on this curve or very close to that curve, this entire curve is known as line of stability, or sometimes we call it stability curve. Stability curve. Either you say line of stability or you say stability curve. It is this blue colored dotted curve for which initial part superposes on n equal to z line. Correct? Fine. Mind well, this is the graph of z versus n. This is the graph of z versus n. Okay? Fine. Now let us see what is called mass energy or mass equivalent energy. Tell me, Mr. Einstein had given special theory of relativity, but before he gave this theory, people were treating law of conservation of mass and law of conservation of energy separately, because they were not knowing that mass is equivalent to energy. Very first time Einstein had proved in his theory of special theory of relativity that mass is nothing but that quantity which is equivalent to some amount of energy. That mass which is having some, which when converted into energy, you can call that mass as mass energy. Though it is a mass, but it is equivalent to some amount of energy. He proved that if m amount of mass is converted into energy and that energy obtained is E, then he had proved very first time the relation between mass and energy, which is famous, E equals to mc square, called mass energy conversion relation. E equals to mc square. Correct? At that time this mass you may call simply mass or you may call it as mass energy, because this much mass means this much amount of energy. M amount of mass and mc square amount of energy, both of them are equivalent to each other. I repeat, m amount of mass and mc square amount of energy, both of them are equivalent to each other. Fine. Now, where c is common velocity of light in vacuum, you know very much, 3 into 10 raised to 8 meter per second. Fine. Now let us see what is called 1 electron volt, shown by symbol small e capital V. See, in the study of atomic and nuclear physics, we require very small unit of energy, which is called 1 electron volt. How much is that energy? I am showing you. Suppose these are the 2 points A and B. Say point A has positive potential, point B has negative potential. Potential difference between these 2 points is suppose 1 volt. And now 1 electron is passing from point A to point B. At that time, electron has to do work because it is going from higher to lower potential. And when electron itself has to do the work, means it will have to spend its kinetic energy. So when electron is going from here to here, the kinetic energy of electron will decrease. That's why change in kinetic energy is negative. But if electron is going from here to here, work is done on the electron. Because work is done on the electron, its energy would increase. So there is increase in kinetic energy of electron. That's why I am writing delta K equals to positive. But one thing is sure, whether electron is moving from here to here or from here to here, there will be some change in its kinetic energy. And that is why the electron volt unit is defined this way. Change in kinetic energy of electron while passing through a potential difference 1 volt is called 1 electron volt. But you may ask, how many joule? Very simple. 1 electron volt is 1.6 into 10 raised to minus 19 joule. How would you prove it? Don't you know this small formula? W equals to VQ, where V is potential difference, Q is charge. Tell me, what is potential difference? Work done on unit charge. Work done on unit charge. On unit charge, if V amount of work is done, then on Q amount of charge, how much is the work done? W equals to VQ. Right now, potential difference is 1 volt. Charge is charge of electron. For 1 electron, what is the magnitude of charge? 1.6 into 10 to the minus 19 coulomb. This into this, answer is 1.6 into 10 to the minus 19 joule. That's why this much energy is obtained or lost by 1 electron when it passes through a potential difference of 1 volt is known as 1 electron volt. Change in energy of an electron while passing through a potential difference of 1 volt is called 1 electron volt. 1 kilo electron volt, kilo means 10 raised to 3. 1 mega electron volt or million electron volt is 10 raised to 6 electron volt. 1 billion electron volt or 1 giga electron volt is 10 raised to 9 electron volt. Million or mega means 10 raised to 6, billion or giga means 10 raised to 9. Got it?